I have a confession. I don't normally pay much attention to Globebusters, but occasionally I do go over there and just see what kind of videos they had. And they had one on Kepler 3 days ago that kind of tickled my fancy a little bit, and I thought it might be worth having a look at. And I'm glad that I did because this is a great teaching opportunity for physics. Now, when you're a science educator like I am, you do a couple of things. First of all, you put out good science. You talk about how science works. And then you also can have a look at examples of where science doesn't work very well based on how it's presented, and try and show how it could be presented better. Now, one of the things about physics is that there is an awful lot of math involved in physics. And math, when it comes to physics, is not simply memorizing formulas. If that was the case, I'd be screwed because my memory sucks. But it's what the math says to you. Does the math speak to you? And that is what we really do in physics. We look at relationships that are described mathematically. And Kepler's laws are a very good example of this. So what I'm going to do is I'm going to let the guys over on Globebusters go over Kepler's 3 laws of planetary motion because they do a pretty good job. And then I'm going to just interject once in a while and talk about a couple of things that they're not doing probably quite as well as they could. So let's go ahead and have a look. So I'm gonna go ahead and pop out of my window, and let's just go over to Globebusters.
Planet, and we'll tell you exactly what it's going to do.
Yeah.
You don't throw anything else in there. You can't put another moon in there.
Can't do it. Can't do it.
The greatest supercomputers on Earth. It just goes all haywire and wacky, and things start getting flown out. And yeah, it's nonsense.
Now keep in mind, they've come up with solutions to impose what the predictions would be, but they don't actually have a way to solve it. It's not.
All right, just to kind of get everybody up to speed, what they're talking about is the 3-body problem, which is something the flat earthers love to talk about. What they don't realize is that we don't solve the 3-body problem continuously. What we do is we break it up into small segments of time. The moon's here, the earth is here, the sun is there. Okay, here's how they're interacting at this moment. Then we advance it a second, and we see how they interact in 1 second. That's the way you solve these things. You break them up into increments of time, and that's kind of the basis of calculus as well. But let's go ahead and continue.
Like an actual solution in like a meaningful way that the system is explained dynamically. So there is no actual solution to it, but they're super involved in the role play, and the math does work out. So we're going to dive into specifically how that interaction works out and what these constants are and what you could do with constants and ratios, because it turns out you can define all of physics based off of some agreed upon ratios and go from there. So it'll be interesting to go through that. So let me start the screen share here, and we'll start with the astronomical implications of applying big G to the sky, which is derived from little g. But Shane will be covering that part of it here. So.
Okay, now I've actually got studio mode going, but something popped up on Discord here real quick. Kind of confused me a little bit. That was actually their Discord, not mine. I was trying to turn it off. But so right now we've already set up a major problem with flat earthers, and that is, did you pick up what they said? These agreed upon constants, okay? Constants are not agreed upon. Constants are measured values. They are experimentally determined. Cavendish, when he did his work, didn't agree upon big G. He didn't really get involved with big G, but I'm using that as an example. Big G comes out of his experimental results. Yesterday, when we were doing Coulomb's law and looking at the separation of like charges, we actually experimentally measured that separation, calculated the angles, and then calculated the charges on these little aluminum balls that we had charged. So these are things that we don't get together over coffee and agree upon. These are things that we actually determine. So let's go ahead and continue and see what he's got to say.
Screen share.
Some of my favorite topic, dude, because this really strengthens our position, and most Globers who argue it don't know this level of detail on it. So it's fun to educate.
Yeah, once
Also,
you
there's
guys
some-
really started digging into it, I mean, the arguments that were had before, it was not so much getting into the nitty-gritty of the equations and all that kind of stuff. Once you two came along, and, in Austin, I mean, it's been a totally different, like, they have nothing to say anymore. Like,
Well,
there is no rebuttal.
They still
Dude.
say flirts don't know how to math, though.
Yeah, they
say all the
they still
time,
they still just say the
and
same things, but yeah, we have a really strong crew, man, and shout out to all the lads and ladettes who are behind the scenes at Ether Cause helping us out with all of this stuff.
Shout out to Whitsitt over there on Modern Day Debate.
Dude, he's out there
crushing
out there
it, right?
out there in the streets.
That was kind of an easy one to debate against them.
Come on, let's get going, boys.
But props to him for going out there and doing it. I mean,
Come on.
Yep.
yeah.
So I remember being asked that very question about Jupiter's moon's periodicity and using Big G in that relationship a couple of years ago, and I was like, that's a good question. I don't know how that works, but there must be something that I don't understand that somehow makes it all magically work, right? And which is a weird position to take, right? Because that's like appeal to infinite possibility or whatever. But as it turns out, a couple years later, we had Dr. Bennett on Whitsitt's channel doing his presentation on science propaganda. And one of the things he covered was the relationship between Kepler's laws and Newton's laws, which is this GMM over R squared relationship, where they're asserting that without knowing the mass of these planets and the gravitational potential relationship between them, they can predict the motion of these bodies with these equations. That's what these equations are supposed to represent for them. So they apply like physical meaningfulness to them in that relationship with the interactions with gravity based on these variables here. This is the big G is supposed to represent the gravitational potential. The big M is a mass of the body that you're using. So if you were using the Earth, you would use the mass of the Earth, and then you could backwards derive what the mass of the Sun would be using the mass of the Earth with this exact same equation, and then doing it outward. Then doing it for other planets or stars or whatever, you would just use M for the mass of the Sun as your constant there, and then the other M would cancel out. Doesn't matter. You don't need to know it, but you could backwards derive it always from this relationship. And it would always share proportionality because it's over a constant here. But we're going to get...
Okay, so let's go ahead and see whether or not maybe we can unpack a little bit of what he's talking about here. Now, it's very true that if you take a spring scale, a calibrated spring scale, and you measure the weight of this coffee cup, you can determine the mass of the coffee cup using a beam balance and comparing it directly to other masses. So by looking at the weight of the coffee cup, you get the force due to the acceleration of gravity. And if you get right down to it, because we know big G, we know the radius of the Earth, we know the mass of the coffee cup in newtons, or the weight of the coffee cup in newtons. We can actually figure out the mass of the Earth from this. And it's a very interesting mathematical issue. And, it's not something that is very difficult to do. It's definitely ninth grade level math. So what he's trying to do right now is he's trying to set this up as being something that's completely unintelligible and nonsensical because it's so unintelligible to him. But let's go ahead and have him explain these laws, because these are pretty good laws, and he does a pretty good job explaining it. Let's we'll interrupt him periodically when he makes some small mistakes.
Into what all this means specifically as we go forward. So Kepler's third law is that the square of the periodicity is proportional to the cube of the semi-major axis of the orbit. So in other words, they're telling you that based on how long it takes something to complete a circuit in the sky, the square of that time is proportional to the length of the semi-major axis of its orbit, meaning it's going to give you the radius of the ellipse, essentially, or the radius of a circle of the orbit if it's a circle. For what we're doing here, it'll be for a circle, so we're going to do pi, but that's the relationship. So in other words, it'll give you the astronomical unit, essentially, right? So it'll tell you how far the Earth is away from the sun, and you could do this all based off of kinematics, because this is all just based off of empirical observation. We're not making any initial assumptions before we do the algebraic swap in, but we're going to go over Kepler's laws first and talk about kinematics. But before we do that, let's define kinematics and
Let's not.
real
Let's
quick.
just keep going. Let's not bother with that. Come on.
They're going to use a little math there. Go ahead.
I say p squared equals a cubed is how that's usually represented, right? When we go with the derivation of it, that's the proportionality represented.
Yes, sir. Yes, sir. All right. So to start us off with gravity and centripetal force and how they're going to relate this to Kepler's laws with periodicity, we're going to take the centrifugal force, which is Fc here, and this is equal to mass times the square of velocity over a radius, and this will give you your centripetal force here. So our centripetal force is equal to the gravitational force there. So Fc is going to be equal to Fg, and we know Fg is going to be equal to gmm over r squared. Now this relationship was applied later, which Shane is going to get into, or how they establish these constants rather. But let's just take it for, let's just say they have these constants, and now we're going to relate them to what Kepler's laws are for how things move in the sky.
Okay, so let's kind of catch up to where we are right now. Now, gravity causes bodies to move towards the Earth. Centrifugal force from the orbit causes that body to move away from the Earth. The definition of an orbit, at least so that you can wrap your head around it, is where the centrifugal force equally balances the gravitational attraction of the Earth. And as a result, the body just keeps going around the Earth. That's the way satellites work. So that's where he's getting this from right now.
Okay, so the centripetal force here is equal to the gravitational force here.
Good.
Right, because Fc and Fg are equivalent. So as we're going through this algebraically, we're going to reduce them down into into the smallest form that we can, and we're going to show that the mass in the equations cancels out, and none of this is actually dynamic explanations of anything, but it's all going to be a ratio of periodicities. But we're going over, a ratio of periodicities with respect to constants, and we're going to show how all that relates and what that means as I go through the equation here. So anyway,
relating centripetal to the gravitational is key too, because that's first of all the circumstances in which the mass cancels out. It's also what they have to do dynamically all the time whenever they use gravitational force of any sort in any circumstance. So it's key that we use it here, and because it's the only instance in which the mass drops out, but it's how they apply it every single time. As far as tides, gravitational interference, all of that, they have to use centripetal and gravitational as the same.
Okay, so basically that is a bunch of dirt, but where he's going with this right now is he's just going through this equation, and he's doing a pretty decent job of it, so let's let him continue.
Yep. Okay, so when we start doing the old algebraic shuffle here to cancel out the masses, we could reduce this down. Now we've got velocity squared over r is equal to gm over r squared. We can start canceling out some of the r's here, and we're left with the velocity squared is equal to gm over r.
Okay.
Now we can keep going even further now, and we can break this velocity. So this is how Kepler turned the periodicity into an orbital circumference. So we got this velocity here, and we got equal to gm over r. It's the gravitational potential times the mass over the radius. And then we have, on this side of the equation, we have velocity, which what is velocity? Distance, time. So the circumference is going to be 2 pi r, and then the time is going to be the periodicity of the orbit. So now
Correct.
we can start getting like geometric properties out of this. So now v squared is going to be equal to 2 pi r over the periodicity squared. Now what we can do with that is we can rewrite that as 4 pi squared times r squared over the periodicity squared is now equal to gm over r squared. So this is how we turned a velocity into the radius, or a portion of the radius, rather. All right, now we can get rid of these r's, so we can multiply by r's to cancel them out. When we do that,
Okay, I'm going to stop him right here, and the reason that I'm going to stop him is that he is taking this a little further than it actually needs to go. So if you look right here, what does this equation equal? You should be able to see my mouse. Apparently you're not. Is that correct? Give me just a second. Let me see whether or not I can see get this mouse. Doesn't give me something to show the mouse. But if you look in the upper left corner, you see r times 4 pi squared r squared over t squared. All right, go ahead and multiply those r's together. So you're going to get 4 pi squared times r cubed over t squared. Okay? You can leave it right there. And then what you do is you take that 4 pi squared and move it over to the other side. But let's go ahead and I'll show you what I mean by that here in just a second. So give me just half a second here.
we are left with 4 pi squared times r cubed over over t squared is equal to gm. And we can divide these out to get rid of the 4 pi's. So we can keep this going.
Okay, so we'll stop right here. And if you look in the upper left, here is the relationship that we want. We've got r cubed over t squared equals g times m divided by 4 pi squared. Now the key thing here is that g is a constant, m is a constant, that's the mass of the Earth, 4 is a constant, and pi squared is a constant. So we have two variables, we have a ratio of two variables related to a constant. All right. Now for those of you that remember the ideal gas law, for example, if you look at the derivation of Boyle's law, pressure 1 times volume 1 equals nRT equals pressure 2 times volume 2. That's the purpose of Boyle's law. You're comparing two states, a radius and a period here, against a constant. So if, for example, I look at the height of the ISS is about 420 meters, and that's above the radius of the Earth of 6371, excuse me, I said meters instead of kilometers, I meant kilometers. So the radius of the Earth is 6371 kilometers, and the ISS is a further 420 kilometers further. So now we have a radius to the center of the Earth. Now, the period of the ISS is about 92 minutes. So we know this. Now, we can look at the period of the moon, for example, and with a little algebraic manipulation, we can calculate the distance to the moon. But we have to know one first. So what he's going to try and do, and what these guys are trying to do, is they're going to try and argue the meaning of big G. Maybe they're going to argue the meaning of pi. Who the hell knows? Let's just replace GM over 4 pi squared with a letter. Call it P. That P is going to be a constant. And what we're going to do is we're going to take a radius over a period and compare it to another radius over a period, with both of them equaling the same constant. That's how we get this ratio working. And that's something that they seem to misunderstand. They're getting a little confused here by trying to put variables on both sides of the equals sign. Show you what I mean with that.
And then we're left with the radius cubed over the periodicity cubed is equal to GM over 4 pi squared. We can invert that and rewrite it, cancel out the r's, and then we're left with just the periodicity is equal, or the periodicity squared is equal to 4 pi squared over GM, which is equal to
multiplied by
cube of the semi-major axis, the radius. So all we did there is change how long it takes for something to complete a circuit in the sky into a function of what would the distance be if it was traveling and how fast it would have to be to get that. So that's why when you that's when you go through and cancel everything out. When we were talking about the mass canceling out, right? The important factor, that dynamic cause, isn't relevant. This is all just a ratio of the periodicity. The only things that change in this equation are the periodicities, because what you're doing for periodicity. So how'd they get the distance to the sun to the earth then?
Okay, so once again, let's go see what they're actually doing here. Now, let's look over on the right side of the screen. I'm going to pop off my image a little bit so that you can see it a little bit better. But if you look on the right side of the screen here, you're going to see t squared equals 4 pi squared over GM times r cubed, okay? And underneath, they're using different letters now. So instead of T, they're using P for period. And instead of R, they're using A for axis. But you see how these are basically, what this is doing is it's relating the period variable to the axis variable or the radius variable. Now notice that you have this little proportional sign on the bottom, but you have an equals sign on the top. The reason for that is this 4 pi squared over GM. That's called a constant of proportionality. And that converts it from being a relationship to being an equals sign. Hopefully that made sense to everybody.
We'll go over that in a second. But the only thing that changes in here for each scenario when you're analyzing how long it takes for something to complete a circuit in the sky, whether it be the sun, the moon, Jupiter, the Jupiter's moons, etc., all of that that's the only variable that changes in here. So because everything cancels out and it's just a ratio of constants over the periodicity, that's why these work out proportional. That's why when you apply Earth's mass and you can backwards derive what the sun's mass would have to be, and then you use the sun's mass as a constant for everything. That's why all these things all work out, because it's only based off of the periodicity. Everything else will you can backwards fill in. Once you have the initial baseline constant to use, you're good to go. So Shane's going to be breaking down specifically big G and M, which is in relation to Cavendish. But like I said, we're just going to assume these constants for now and say, now that we have them, what do we do with them? How do they work? How does everything apply? Right?
Okay, so let's go ahead and just have a quick look at it. Now, as you may recall, let's use the example of the ideal gas law. Okay, so PV equals nRT. Okay? If we hold the temperature the same, the number of moles, we don't change the amount of gas that's in it, and this, of course, is the gas constant. So this, we're going to make a constant. We'll just call that K. So PV equals K. Now, if we have a gas in state 1, which is P1, V1, and say we decrease the volume, okay, we're going to end up with something that's P2, V2. Now, since they're both equal to K, they're both equal to each other. So if we want to figure out what the new pressure is going to be, we're going to take P1, V1, we're going to divide it by V2, and that will equal our new pressure. The same thing happens with Kepler's laws. Now, if you look at T squared divided by R to the cubed. Let's make this T1 and R1. We're going to call this the ISS. So T1 is going to be 92 minutes times 60 seconds. And R1 is going to be 6,371 kilometers plus 420 kilometers, because it's 420 kilometers above the surface of the Earth, and that's the radius of the Earth, times 1,000. Now, if we look at something, let's go ahead and do something here. Suppose we wanted to find out how fast the Earth would have to rotate in order to be weightless at the equator. Okay? What's going to happen here? This is going to equal X minutes, okay, over a radius of 66371 times 1,000. Now, if we bring this over to here, like so, if we multiply both sides by 6371 times 1,000, what we're going to end up with is the number of minutes that one rotation of the Earth would equal. Now, I'm going to let you guys go ahead and do the math for this, but it's going to work out to 84 minutes. So if the Earth rotated once every 84 minutes, about 17 times faster than it does right now, you would be in orbit standing on the ground at the equator. You would be completely weightless because your centrifugal force would equal the gravitational force. Hopefully that made sense to everybody. I have my slide rule, Clive. Well, let's go back and just listen to this a little bit longer.
What if the mass of the Earth is off or whatever? Well, it doesn't matter. It's still going to share the same proportionality ratio. The calculative values of everything else is just going to change proportional, and it's still going to work out.
Notice that mass is not part of any of these equations. And why is that? You know, mass was already set as part of the constant above, okay? So here's a constant, P. The mass of the Earth is here, okay? So none of this stuff here, you don't even need to know any of that. All you need to know is that this is equal to a constant. And as a result, if you're dealing with the same body, that's also equal to a constant. So you can change the radius and it'll change the period. You can change the period, it'll change the radius of the orbit. It's just as simple as that. That's the power of the math.
So it would have been whatever they told us it is. So is there anything is there anything you want to add to that, Shane or Zach?
I think it's really did a really good job breaking down what is important is not what they say it is, right? The constant that determines the ratio based on a density inference that they measure later is not the important part of that. The thing that they use it for is periodicity and then the constant. So they can replace it and they can use that same formula for, say, building the solar system, right? Just because they don't know how all bodies interact together and they mathematically can't figure it out because it's impossible, doesn't mean they can't play pretend and then do like one simple series of two body problems at a time so that they get like, the sun and Venus, the sun and Jupiter, the sun and Mars, the sun and Earth, put those in a neat array and go, look, we've used Newton's law of gravitation to build the solar system. And in reality, none of that works. The masses aren't real. They actually would cancel out. They have no actual way to determine the stellar masses of anything except for the algebra that we just went over, including the derivation of Newton and Kepler's third law, and then they use algebra to plug in those masses, and then they use that algebra equation to be like, look, now we can calculate the mass of the whole world. And it's insane, and it's never worked, and it's, of course, when the mass cancels out of the equation itself, how can it, one, be the dynamic cause of everything, and also be the standard candle from which you weigh everything in the world?
Oh my good Lord. Did anybody actually listen to that crap? This is a guy who has absolutely no idea what he's talking about, but he's very glad to talk about it. What is Kepler's law used for? Kepler's law is if you take the distance from the Earth to the Sun to be 1 astronomical unit, you don't even have to know what it is. Okay? You can sit down and say, well, the Earth orbits the Sun once every 365.25 days or so. Okay? And that is the orbital period of an orbit with average radius of 1 astronomical unit. Then you can sit down and say, okay, well, it takes Mars 678 days to complete one orbit. And simply knowing that will tell you how far Mars is from the Sun in terms of 1 astronomical unit. You can calculate how many astronomical units that radius would be. And it's actually not that difficult at all. Now, a lot of people are picking up on the fact that Kepler's laws don't really apply and can't exactly calculate a radius on a non-circular orbit, and that is correct. Okay? That was a problem that they ran into in 1800 when they discovered Sirius, which is the first asteroid in the asteroid belt that they discovered. It's actually a dwarf planet. But in any event, what happened was they saw Sirius with telescopes, and they were able to track Sirius through the night sky. But they reached a point where Sirius started going into the daytime. It went into the daytime side of the Earth, and they could no longer see it because the sun was out. And the problem that arose is, how were they going to find it on the other end of the orbit? So when it started coming back into the night side of Earth, how were they going to be able to find where it was? And a mathematician by the name of Gauss came up with a solution for it. And these are called orbital elements. And they're commonly referred to. Yeah, I know. For some reason, the audio and the video sync is off a little bit. It just happens to do that once in a while. Just kind of bear with it. Roll with it, man. Roll with it. So where was I? Okay, so the orbital elements. Now, an orbital element is a series of 6 mathematical terms, and they are in 3 groups. The first group looks at the shape and the size of the orbit. So how large is the orbit, and how off of perfectly circular is it? How elliptical is it? Okay. The second set of orbital elements determines, okay, well, what is the angle of the orbit? And is it twisted at all? Does it go up and down? Is it twisted? So that gives you the direction of the orbit in space. And the third set, the 5th and the 6th orbital elements, have to do with where the body is on the orbit. So by getting these 6 orbital elements, I can find an asteroid with my telescope to within an arc second or two. And that arc second is not due to a problem with the math. That's due primarily to the pointing ability of my telescope. The accuracy of my telescope to point to a specific location in the sky is only down to about 3 or 4 arc seconds, which is still pretty good. It's in the middle of a very, very large field. If those of you that have seen me run the telescope, you know that I can pull up crosshairs. And those crosshairs, basically are a big cross, and then they've got a set of concentric circles in the center. And when I look for satellites, I very consistently can put the satellite just off the crosshairs, well within that inner circle. So they're very, very accurate, and it's very easy to find objects in the sky by knowing the Keplerian orbital elements of that particular body, be it a satellite, an asteroid, a planet, or anything else. So that's where we are. So let's go on down and maybe have a look at these guys for a little longer and see what they have. Now, are you getting an off sync with the video that I'm playing, or is it just me that's a little bit out of sync here and there? Look, Godzilla!
Well
How
said,
the nervous
man.
laughter.
Well
And
said.
they seem to get away with it because the math looks so daunting and hard, right?
Actually, the math isn't all that hard. We get away with it because it works.
Because they use all these letters and all this stuff, it's not actual numbers that they're, portraying.
Ratios work, right? So
Yeah,
what are we gonna do?
Exactly.
Did he just say that it wasn't real because we used letters instead of numbers? Just contemplate that for a moment. That's long enough.
It's a way to describe something that you're seeing, not what's causing it. And that's it.
Yeah, they built all of cosmology off of it, off of that, trying to relate what they measured on the ground and applying it to the sky, and then having dynamic causes. I mean, like the amount of power that they gave them philosophically to people. I mean, imagine you could look up at the sky and go, not only can I predict where that's going to be, but I can tell you how much it weighs. Yeah, and they're like, what? Why?
They've gone way beyond that. Now they're saying, do you see, well, you can't see it with your naked eye, but there's a star out right here, 2,000 light years away. And it has helium gas going around it.
Okay, so we can't see stars that are 2,000 light years away. Interesting. Interesting. I know that the Great Orion Nebula is, at least as I recall, it's either 1,300 or 1,600 light years away, and you can see that pretty easily with your eyes. You certainly can see it with binoculars, much less a telescope. So apparently not being able to see them with your naked eye means they're not real. Interesting. Interesting. Yeah, okay. And as far as looking at whether or not there's helium or hydrogen, you can literally see hydrogen using a hydrogen filter. You can see the oxygen, you can see the sulfur. You can literally see those in a photograph. As far as, doing spectroscopy on them, of course you can tell what element they are. That has nothing to do with Kepler. I don't know why they're throwing that out other than to try and throw some more garbage against the wall to see what sticks. It just amazes me. Their debunk style is so random. It's just shockingly immature and juvenile.
Around that planet. they'll tell you what gases are on these planets that you can't even see with your naked eye.
Yeah.
It's nonsensical.
The proper historical context, though, is Kepler had observable laws from making observations. He could tell you where everything in the sky was going to be and when it would be there. And then Newton came along and was like, "Oh, interesting work. I see what you did there. Have you heard of centripetal force? No? Well, guess what? Gravity actually makes everything one. Here's some mass. I'll put it in the equation. Did you see my algebra? And then there you go. That's the historical context."
Okay, let's put this in a little better historical context. Kepler derived his shapes of orbits and stuff by direct measurement. All right. He directly plotted the position of Earth and the other planets. And that's how he derived his laws. The thing that Newton contributed was the mechanism as to why it happens that way. You see, I don't know if you guys have been watching my History of the Flat Earth series, but one of the things that I talk about is that the Earth has been known to be spherical for about 2,300 years. But for a couple of thousand years of that, right up until Newton, there was a lot of controversy as to whether or not it was a geocentric solar system or a heliocentric solar system, because observations could account for either of them. And, either of them worked. But neither of them had a mechanism that would favor one over the other until Newton came along with gravity. And by understanding how gravity works, that gave us a mechanism for the heliocentric solar system, and that's why we realized that it was a heliocentric solar system instead of the Earth at the center of the universe and everything going around it, except, of course, for the planets, which were known to go around the sun. But it was thought that since the planets went around the sun, except, of course, for Earth, and the sun went around the Earth, that somehow that was still geocentric. But, the idea that the solar system could be heliocentric dates back to who was it? Aristarchus of Samos back 2,300 years ago. But it wasn't the predominant theory at the time. The Aristotle and Ptolemy, with their geocentric universes and solar systems, were the predominant thought back then. Again, until Newton came along, and just settled the issue. So let's go ahead and get back here.
Context for what we're showing you is that's how Newton came along and solved the problem of the dynamic cause of everything. Right? Crazy.
And all Kepler did, like an analogy to that would be like watching a movie and then watching a movie with someone else and telling them the ending.
Or that I wrote the ending and here's what's going to happen.
Here's what's going to happen. Yeah, exactly.
Yeah. So a few more things to note on the solar system and the mass of the sun. So everything we know that how they calculate everything is you can basically ignore this is how they solve the three-body problem, right? For one of the ways they'll say is that you can ignore the mass of everything else because it's not going to influence anything over the mass of the sun because it's so massive. So everything in the solar system, where the mass cancels out in the equation and it doesn't affect it at all, you can, you can. They say that that's because of the mass of the sun, right? But when you put the mass back in the equation, it changes it by an imperceptible amount. It's 0.1%. You're not gonna, for an orbital circumference of, they'll say that like Saturn is 800 million miles away from the sun. Okay, dude. So there's a 0.1% difference in that if we put the mass back in. Okay. Well, I'll be sure to. Well, man, you really convinced me now.
Again, they're trying to go back to this three-body problem thing that they don't understand. I'm not even going to address it any further. The reason that the mass of the satellite doesn't matter is because those little m's cancel out, and they don't have any effect to the equation or the ratio specifically. Again, they're looking at it as trying to figure out the mass of the Earth, not knowing the mass of the Earth, not knowing the radius to the satellite. and not knowing the speed of the satellite. That you can't solve a multivariable equation with too many variables. You just can't do it. If you have two unknowns, you need two equations to solve for that. And that's just, very, very basic math. And that is a problem that we're running into with these guys, is that the math doesn't speak to them. They don't see what the math is telling them. And that makes it very difficult. What they're doing is they memorized a couple of equations. They wrote them down. They're throwing them out, and then they're giving their own meanings to those equations. They don't comprehend the idea that if your little m cancels out, it doesn't matter. It just doesn't. And they don't get that. So, the air temperature in Hunan, China does not affect the audio quality of this video. Okay? It is a completely different matter that has no bearing whatsoever on the bandwidth out of my house today, which apparently isn't all that great. The math just doesn't talk to them, and they don't understand the language of mathematics, and as a result of that, they're listening to a movie in Czech with no subtitles here. So let's go ahead and continue.
No, it doesn't. They're like, we can solve a Lagrangian and it'll change the. Okay, man. Yeah, but can you really? Does that matter at all? No.
You don't know what negligible is by telling me you don't know what negligible means. That's
You're right. You tell me you don't know what it means by reiterating it like it's a big difference. No, yeah, that's exactly the point. So you might hear something like, what if we add the masses back in, or you need to solve a Lagrangian, do it, and then tell me the difference and let me know how we're gonna confirm that. You could certainly calculate it for sure, but in terms of explaining where that thing is gonna be a year from now, you don't need to Lagrangian it. You can just use.
Well, that's exactly what they did with Cirrus. They actually predicted where Cirrus was going to be when it came back into the night, and they could view it again. Another example of where they used Kepler to make a prediction was the discovery of Neptune. Okay? Neptune was discovered due to the detection of gravitational abnormalities that suggested that there was another body out there. Okay? And then they looked specifically where that body was supposed to be. And then, lo and behold, there was the planet. Now, granted, that's a little bit different from Kepler, but the same idea. And I use Keplerian orbital elements to find satellites and asteroids, and I'm very successful with doing it because I can literally point directly to where they are, and they're there right in the center of the field. So let's finish this up, and then I'm going to go ahead. We'll probably go for a few more minutes. Hey, Phil. Hope things are going well on your end, Phil. Haven't heard much from you lately. I just want to make sure everything was okay. We're talking about Keplerian orbital elements and getting a physics lesson from Globebusters. So, let's go ahead and continue.
The periodicity that everyone else used, so it's fine. But, they do like to...
Hey, Phil, apparently math has letters in it to be confusing to the lay public. I just wanted to let you know that in case, that wasn't really clear on you. That's why we use letters in math, is just to confuse people that don't have math.
To play in their Cartesian coordinate system and act like they can pick out any defined point in three-dimensional space.
Yeah, we do that all the time.
Coordinate system, so that's a lot of fun for them. So anyway, we'll get back to
we actually do
showing
that
this
all the time.
relationship again, just to kind of reiterate the points here in a more visually aesthetically pleasing manner, perhaps one would say. I would say that, but I'm biased because I made it.
I love this one. Yeah.
All right.
Say it.
So we got our starting FC relationship for centripetal force, and this is of course equal to the gravitational force, which is going to be equal to GMM over R squared, and we got our pi in there, but you can reduce that out and just anyway. So this is good. So our periodicity is going to be equal to our semi-major axis cubed. Now what you would do here, say perhaps we have a guy with some lead balls in his shed, right? He measures the gravitational potential difference between the Earth and these lead balls. And
Oh dear Lord. All right, everybody, let's all say it together. Did Cavendish measure the gravitational attraction of lead balls to the Earth? No. He measured the gravitational attraction of lead balls to each other. He deliberately designed the experiment to take out the gravitational attraction of the Earth. That's why he did it horizontally like this instead of up and down. Okay? These guys have no idea where the gravitational constant came from. Okay? Another thing that you'll see right there, see where it says 30 kilometers per second mandatory, never experimentally measured? Okay. This is the same guy who demonstrated that you could measure the length of an orbit by multiplying pi times twice the radius, or pi times diameter, and then you could get the orbital velocity by dividing that by the time it took to make one orbit. So he understands this, but doesn't know where the 30 kilometers per second of the Earth's orbit came from? Okay. I'll tell you what. You guys go ahead and look at Globebusters from this point on. And let's see. I've got a time here of 41 minutes, 34 seconds. Because quite frankly, this isn't worth my time to even look at anymore. Because now they're just kind of going off the rails. They started off pretty good. They did a pretty decent breakdown of where Kepler's law, third law, came from. Okay? And then they absolutely went off the rails and lost it. That's because they memorized the math, but didn't know what the math meant. And I think that was the big point of this particular live stream today. Again, like I said, as a science educator, there are two things that I do. First is I explain science. The second is I show where people go wrong in their thinking about science. And here's a good example of that. We've got mathematics, and they don't know what the math says to them. They have no idea what that math means. They're just writing out the formula and then applying their own meaning to it, which isn't the way you do that. So, unless anybody else has anything they want to talk about today, I've got a few things that I've got to get doing, and this would be probably a pretty good time to cut off. I don't like doing live streams more than an hour, and we're at 55 minutes right now. Okay, people that do 12-hour live streams are just trying to get super chats and get income. I do these live streams because I want to sit down and interact with my viewers and give them a chance to ask questions and things like that. So I'm going to go ahead and cut the live stream now. Take a moment, have a look at the Telescope Fund. We're getting ready to make another payment on that. If you want to become a channel member, or make sure that you are subscribed to the channel, go ahead and do that. This is a great time to go hit that little button. And in the meantime, I am going to be working on my final part of the series on the history of the flat Earth. We're going into the religious anxiety of the early 19th century, right around the time of the Industrial Revolution, where people suddenly began to rebel against the humanistic approach of the Enlightenment, which produced Newton and a lot of these other things, the transit of Venus, etc. And they were trying to get back to that, and a lot of cults formed from that. A lot of new religions formed. There was a particular cult, a commune type thing in the UK that advertised for a secretary who came in and ended up taking over the commune and driving them in some rather interesting directions. In one case at the point of a pistol. That gentleman that answered that advertisement for a secretary was a guy named Samuel Robotham. And then we're going to start talking about Zion, Illinois. We're going to talk about a cult down in Florida that was a concave earth cult. And we'll have a little bit of fun and finish it up. And we'll end up with the origins of the modern flat earth movement. So until then, we're going to let you guys go, and I'll see you again a little bit later. Take care, everybody. Thank you very much for stopping by. I do appreciate it. We had quite a few. 170, 180 people at one time. We're still at 160, and it's been an hour. That's pretty cool. Well, take care, everybody.